Hello, thank you for joining the Texas Instruments New Product Update webinar. Just a reminder that this is a weekly series every Thursday at 10 a.m. Central. A few quick announcements before we get started. This webinar will be recorded and available online at ti.com/MPU. All phone lines will be muted, so if you have questions, please use the chat box and we will try to answer in real time, or you can contact your TI salesperson or field application engineer. Today's topic is 4-channel synchronous vibration sensor reference design featuring ADS127L11. I will now pass it over to Ahmad Noman and Michael Saul for introductions.
Hello, everybody. My name is Ahmed Neumann. I'm a system engineer in the Factory Automation and Control department in TI, resident in Germany.
Hello, everyone. My name is Mike Saul. I'm a product marketing engineer in the Precision ADC product line at TI, based in Dallas, Texas.
So today we are going to walk you through our new design, IEPE, 4-channel IEPE interface. We are going to introduce first the system overview, then the IEPE sensors. Then we're going to introduce the 4-channel wideband interface design, along with the new ADC ADS127L11. And finally, we're going to represent the test setup and results, as well as going beyond only the capture of the data to talking about how to transmit and process the data on the edge. So if we started by looking at the typical vibration monitoring system, we see that the vibration sensor attached to a monitored machine or equipment, the sensor converts physical vibration into electrical signal. This electrical signal goes through signal conditioning and data acquisition module, which converts it to a data stream that can be processed either at the edge or transferred over network protocol like Ethernet to a higher level. Then analysis software is running either on a PC, industrial PC, or cloud to process the vibration data either in time domain or frequency domain and compare it to a healthy patterns to detect anomalies and faults in the monitored machine. In comparison to temperature and current sensing, vibration sensing is more demanding. First, it requires specialized sensors. Most common vibration sensors are accelerometers. Major types of vibration sensors and their typical performance ranges are shown in this slide. We see on the right the servo accelerometer, and those are the most accurate and high dynamic range, however with very low bandwidth, and they are typically used for navigation. Charged piezoelectric sensors, where vibration is converted to tiny capacitive changes, is generally reserved for the use in very high temperature environments and harsh environments. Piezoresistive, which we see in the middle, those are limited dynamic range and are more common in crash tests. They are on the lower price range and lower performance range as well. They are more suited for impulse detection. On the factory floor, or the process plant, we typically see two types of sensor: the capacitive MEMS sensor, which are offering lower to medium performance and bandwidth, but in a very small footprint. They are also used in automotive, like in airbags. As you can see, the dynamic range in the is going to like 90 dB only. And more commonly is the IEPE, which is the industry standard integrated electronics piezoelectric accelerometer. And this type of sensor is optimal for performance it offers the optimal performance with respect to dynamic range and bandwidth. We see here bandwidth is going to 50 kilohertz and dynamic range over 120 dB. The reason for this requirements high demanding is that the sensors are typically attached to machines or equipments in a very noisy environment regarding vibration. So the spectrum is full of non-essential tones and vibrations which are not what we are looking for, and we need this high dynamic range and wide bandwidth to allow us to dig into the spectrum and pick the tones that matters to the specific machine health. I'm going to elaborate a bit on the IEPE sensor, as it's the industry standard of vibration sensing. The interface between the IEPE and the modules are standard. So all IEPE sensors can work with any IEPE interface module, regardless of manufacturer or brand. The IEPE sensor structure is shown here on the upper left. A sturdy sealed metal casing encloses a suspended mass attached to the casing through a piezoelectric material. When the casing accelerates, the tension forces on the piezoelectric material changes its capacitance. This capacitive change is amplified with an integrated electronics, which is in the actual sensor, and that hence comes the integrated electronics. That means capacitive sensor, so capacitive transducer on top of integrated electronics. The simplified circuit of the simplified circuit model of the IEPE sensor is shown on the middle here, on the upper middle. The sensor is basically a transducer followed by a charge amplifier. The charge amplifier is powered through the cable, the 2-wire cable, which is connected to the module. You will see here the DC current source powering the amplifier. The amplifier output is a voltage signal that follows the vibration input, and that's seen on the bottom here. If this is our measurement range in G, acceleration of gravity, on the right here we see the voltage output of the sensor, which is the voltage input for the module. And to allow the single supply operation of the modules, the IEPE standard is adding a DC voltage to the output signal. So the sensor is adding a DC voltage called the V bias. And this DC bias is typically blocked by the AC coupling. So as we can see on the bottom right here, we have the frequency response of the sensor, which shows a flat response over the frequency of operation, going down to fraction of hertz up to 15, 20, or 30 kilohertz, followed by a resonance frequency of the sensor itself. So the useful range is up to something below the resonance frequency. Typical specification of a sensor includes the output range, the bias voltage, frequency range, the noise, excitation current required, typically 2 milliamps or more, and the dynamic range. So the application we just talked about is not the only application for vibration monitoring. Applications extend beyond the factory floor. Actually, it goes to large structural monitoring, like we see here, wind turbines, monitoring moving parts in automotive applications or industrial transport, large HVAC systems, also monitoring the moving parts. So wide range of applications for vibration monitoring. So after introducing the IEP sensor and the application, we can delve into our design, which you can find on ti.com under the name TIDA 010249. The design demonstrates a 4-channel simultaneous sampling, high resolution, 24-bit and wideband, 20 kilohertz. It can also go beyond the 20 kilohertz up to 200 kilohertz IEPE sensor interface. The interface design accepts plus minus 10 volts of AC input and implements wire break and short circuit detection in case of malfunction of the sensor. It has also onboard power, so the board generates the required power from the 5 volt, and it also has the constant current source of 3.5 milliamp required for powering the sensor. The design is based on our new high-speed Sigma Delta ADC, the ADS127L11. So I will let Mike here, give you a closer look on the ADC.
Thank you, Ahmed. This is the ADS127L11. As mentioned by Ahmed, this is the ADC that is used in the reference design he introduced on the previous slide. This is a 24-bit, 400 kSPS, low-power, wide bandwidth Delta Sigma ADC with input and reference buffers. As you can see on the slide in the block diagram, the device has a wideband filter that operates up to 400 kSPS in a low latency filter mode that operates just over 1 MSPS. This device uses an SPI interface and supports a temperature range of -40 to 125 C. Additionally, it's available in a small package size of 3 mm by 3 mm QFN package. The device supports power scalable modes, such as a high-speed mode offering a typical power dissipation of 18.5 milliwatts, and in the low-speed mode offering a typical power dissipation of 3.3 milliwatts. For multi-channel systems, this device can also be easily daisy-chained with SPI communication, so you can create 2 4-channel systems using this device. We also have an application note available on ti.com that shows how to achieve this multi-channel system via daisy chain. Next slide, please. Thank you. To highlight some of the performance of the ADS127L11, it has excellent AC precision as well as DC accuracy. So you can see at 200 kSPS, this ADC offers 111 dB of dynamic range with negative 125 dB of total harmonic distortion. From a DC accuracy perspective, it offers a 0.9 ppm typical INL, or integral nonlinearity, and it also offers low offset drift at 50 nanovolts per degree C, and a very low gain drift of 0.6 ppm per degree C. Next slide, please, Ahmed. Thank you. And now I would like to introduce our newest ADC in the same device family, the ADS127L21. This device went live on ti.com this week. It's a 24-bit, 512 kSPS wide bandwidth Delta Sigma ADC with programmable filters. This device is pin-to-pin compatible with the ADS127L11. The main differences are that it can operate up to 512 kSPS in the wide bandwidth mode and 1.35 MSPS in the low latency mode. Additionally, this device offers 2 additional speed modes, so 4 total speed modes compared to the ADS127L11. Additionally, in the filter configurations, we offer programmable FIR and IIR filters on the chip. So if in your end application you do any type of filtering in the MCU or FPGA, you can now directly upload those coefficients to the ADC for a more integrated solution. And now I will hand it back to Ahmed to further discuss the IEPE sensor design using the ADS127L11.
Thanks, Mike. Coming back to our 4-channel interface design, let's have a detailed look on the signal chain. On the left, we have our plus minus 10 volt signal passing, the cap on the interface, the AC coupling, followed by a 10-to-1 divider after the cap, which implements an high-pass filter and a 10-to-1 scaling. The plus minus 1 volt signal, which is coming after the high-pass filter, is centered around 2.5 volt. This 2.5 volt is coming through the common mode generated by the ADC, buffered to improve the dynamic performance, and going to the potential divider so that we can shift the signal to 2.5 volt required, for the high dynamic range we need for the signal chain. The non-inverting gain stage has a gain of 2 and implemented using a highly linear OPA 2320. It's providing high input impedance and driving strength to drive the fully differential amp. The plus minus 2 volt signal is then converted to a differential signal using the wide bandwidth THS 4551 differential amplifier. The differential amplifier implements also a gain of 2 and a low pass filter of 20 kilohertz, which is required to eliminate the resonance frequency of the sensor. This brings the single-ended signal at the input of the ADC to plus minus 2 volt each and a differential signal of plus minus 4 volt. The 4 volt reference, REF 6040, is used to achieve the highest dynamic range through the ADC. We see also a simple high side current source on the left. This high side current source is implemented by an OPA 4817 quad op amp that implements 4 separate current sources plus a shunt reference, the TLV 431. And the open and short detection are implemented through comparators and hysteresis. And the data from these comparators, because we have 4 channels, 2 comparators each for open and short, we have 8 signals in total. We are collecting data through a shift register and sending that serially to the NPU or CPU. The high compliance current source is powered by an efficient booster, the TLV 61046A. Followed by an LDO, the TPS 7A49, to improve the power supply rejection of the current source at higher frequency. In the next slides, we are going to talk a bit about the current source, the clocking, and the data interface. So 4 current sources are implemented, as mentioned, using a quad op amp and shunt regulators. Each has 3.5 milliamp, so about 16 milliamp with a 24 volt are generated using the LDO. So we are talking about 0.4 watt of power here. The booster at such load is running at 80% efficiency, which means the 4 current sources uses about 0.5 watt. So this is actually constitutes the half of the power required for the whole board. So the whole board runs at around 1 watt. Half of them are going to generate the current sources at high compliance voltage. And we remember that we need that high compliance voltage because of the sensor. If the sensor is generating a high swing signal, plus minus 10 volt, we would need the high compliance. Here in the middle, we see the comparison between AC coupling and DC coupling. We have one channel in the design. The fourth channel shows the DC coupling. For DC coupling, offset cancellation is required, and this is required to avoid the ADC saturation. Offset cancellation is done here through onboard DAC, the DAC 7501, and which is 14-bit DAC. The software provided with the design, you can download from ti.com, has a function to run successive approximation algorithm to search for the best value of the offset cancellation. This also requires sort of like a state of the sensor which doesn't have so much excitation. So like in steady state. Finally, for simultaneous sampling, synchronous operation of the 4 ADCs is essential. This requires two elements, actually. First, the clocks going to the all ADCs, the 4 ADCs need to be synchronized, and this is ensured by using, by using a buffer, low jitter buffer LMK1C1106 after the crystal oscillator. Second, start signal, start sync signal, which goes to every ADC, needs to be sampled exactly at the same time, at the same clock cycle. And this is done as shown here through a simple logic that gates the sync signal with the same ADC clock to ensure that all ADCs are sampling the start sync signal at the exactly same instant. The ADC supports, as Mike mentioned, parallel mode, where the ADCs can run up to 400 kilosample per second for wideband filter mode. Here we require 4 separate SDO signals. In daisy chain mode, we can run through one SDO signal, so we can use the 4 signals typical for the SPI to run all the ADCs. We have here a maximum data rate of 128 kilosample per second. Both modes are supported on the design through assembly option. The same for the clocking. So we have assembly options allowing us to synchronize 2 boards. So if you want to have more than 4 channels, let's say 6 or 8 channels, by using 2 boards, you can generate the clock on one of the boards and use the clock on the other board, which then wouldn't have a crystal oscillator. That's how the design look like. You see on the top left here how the layout is structured. We have each channel, the BNC connector, followed by the signal chain for each channel up to the ADC. In the middle, we see here the clocking, the reference used for all the 4 channels. Here we see the clocking and the buffering of the clock using the low jitter buffer, and the back connection here, the connector is going to our PHY board, PHI. This is the capture card used for all our ADCs, which can be purchased easily with any of our single channel ADCs. On the top, we have the current sources and the power circuits. So in the summary of our measurements shows 17 effective number of bits over wideband. We tested that up to 200 kilohertz. We have high linearity of minus 97 dB total harmonic distortion. We have a wide dynamic range of 103 dB, and all that, as I said, the analog power we need is like 0.65 watt on top of the power required for the current sources. How we tested the board, we actually tested the board 2 ways. For testing the total harmonic distortion and the linearity, we need a very clean source. And of course, having this equipment might be prohibitive. We have such equipment, but the idea we give here to you is getting the PSI. That's a very clean 2 kilohertz source, sinusoidal source that you can actually purchase, very very cheap on our TI.com, and this allows us to test the signal chain with a very clean 2 kilohertz sinusoidal signal. To test the features of the sensor, we have an IEPE, what we call IEPE simulator, which is driven by any functional generator, and allows and converts this function generator signal into IEPE equivalent output. And we see here the PHY board connected to the 4-channel board, and then this goes to USB port where our and PC, which runs our software, dedicated software, which you also can download from TI.com. Here are some captures from the software, shows the performance. We see here on the top right, the time domain signal for 4 channels, and you see the difference in offset, little difference in offset between the channels. The frequency response of one of the channels you see on the bottom, and as you can see, RMS noise with shorted input is around 18 microvolt, and this is actually pretty much the noise of the signal chain, the front end, because the ADC noise performance is way better than that. So the majority of this noise is coming from the front end. This is the PSI software generating our clean source. And on the left here, we see the output of a total harmonic distortion test. As we can see, the total harmonic distortion at around minus 4.8 dB full scale input is around minus 105 dB, which shows how linear this signal chain is. The diagram on the lower right is the ADC synchronization. We are monitoring here the data ready signal, which is generated by each ADC when the data is ready to be transferred. As you can see, we have sub-nanosecond difference here. Actually, it indicates we are capturing the data exactly at the same clock cycle. So here is a more detailed summary of measurement results. Again, I'm highlighting here the 17 bit of effective number of bits over 20 kilohertz, and compliance range, high compliance range of our current source, low power dissipation, which goes around 1 watt for the 4 channels, including the current source, and the more than 100 dB of dynamic range. So we are actually short in time, but I wanted to give a glimpse on our sorry for that. So one question which we might ask, what happens with this data we are generating? We are generating so much amount of data. What to do with this? And here we are actually showing what to do with this data, how to transfer this data. We have actually 2 other boards. One we call the Edge Processing Board, which includes one of our Citara processor, AM243X. This basically connects to the 4-channel board and capture the data from the 4 ADCs. It does FFT, fast Fourier transform for the 4 channels, and can also implement the simple mask detection or quick anomaly detection. And on top of that, it does the transmission over single pair Ethernet. So the board is connected to a second board through a single pair Ethernet with power over data line. So this board is transferring data over the same line, which carries the power required. This goes to a gateway board. The gateway board can serve actually 4 of these boards, and it provides the required power and concentrate the data from all the boards. It then can send this data over Ethernet to a higher level for processing, and on the same time it runs a web server where we can actually monitor through any web connection, monitor the time domain or frequency domain performance of our different sensors. So these boards will come online soon. I just wanted to give heads up that we are not only working on the front end, but we are also looking into the back end, how we are going to process and transfer this data. By that, I can hand back to Mike to comment on the resources available for this design.
Yes, just wanted to end the discussion or the meeting with some of the collateral you can use to get started on designing for condition monitoring, IEP sensors, or other designs that are applicable to this. So we have the reference design that Ahmed shared today, available on TI.com, as well as a vibration sensor design guide available online. And of course, we have the product page for the ADS127L11, which is the precision ADC used in this design. And also, Ahmed shared the precision signal injector evaluation module for generating a clean source. That is also available on TI.com as well. So I would like to thank you all for your time, and I will hand it back to Kelly to end today's presentation.
All right, thank you. And thank you everyone for attending today's MPU webinar. The recording and PDF version of the slides will be available at ti.com/MPU. See you next week for our next topic, Advancing Intelligence at the Edge. Have a great day.